Good morning, Calculus 2 people. So today we're going to continue talking about partial derivatives. We're going to do 9.6, okay, and I can't minimize one. Okay, let's share my screen then, because that's what I really meant to do. So let's just kind of jump into it. Oh, this is not 9.6. What do we want to do? We wanted to do, we wanted to go back and do, we wanted to do 9.5, I believe. 2, 3, 4, 5. There we go, 9.5. That's what I wanted to do. Okay. Let's just try another one here. Okay, let's get a similar question. All right. So the idea here is that we're going to be calculating the total derivative. Okay, now this is a definition. You don't have to worry about this from Calc 1. So this is a brand new type of a thing. So total derivative, all right, is a definition. So if I want the like dz, okay, we are going to, so we have a function of z. We have z is equal to some function f of xy. Okay, so we're going to say that dz is equal to the partial of f with respect to x times the dx plus partial of f with respect to xy of dy times proper dy. Okay, and we can generalize this. So if I wanted, like, I don't know, u equals some function of x, y, z, s, t, u, or not u, but v, w, etc. Okay, it's just going to be a whole big trail, okay, of what's going on here. So du would be the function, the partial of f, okay, with the partial of the first variable times the differential of the first variable, plus partial of f with the second variable, we'll say y here, okay, realizing there's more to it, okay, partial of y dy, plus partial of f, okay, dz with the proper dz there instead of the weird 2 looking thing here. Okay, and that's just the definition of a partial derivative. The definition of a total derivative. All right, and that's what they're asking us to do here. Okay, so later on, this is often how people chase experimental error through a system. So if you've got multiple variables going through here, they want to know, like, what's the total error, what's the total difference in what you should get. And maybe you've got, maybe we've got a temperature, okay, maybe you've got the volume of a beaker, maybe you've got something that you've measured, you've got a pH, maybe you've got a couple of chemicals, okay, and you're trying to measure how much of these things are there, okay. Let's get rid of volume for saying volume of these chemicals, okay. But you could have a whole host of different factors that are going to influence your experiment, right? And they're all going to have some kind of measurement error attached to them. Okay, we usually, there's your measurement error. Okay, it's something that we can estimate. Okay, and then we're trying to figure out, like, well, what's the whole error for the whole system? Okay, like where are we going to be off in total? And that's kind of what we do. Okay, so even like, okay, if we're going to measure a box, right, we've got x, y, and z, that equals my volume. So if I wanted to figure out, like, well, what's the total volume, what's the total error in the box, right? We're going to say, well, we're going to need d of x, y, z over dx times dx. Okay, so what we're doing here is we're figuring out, like, what in your length, say, what's the error here, plus dx, y, z, dy, dy. Okay, and then dx yz of dz times proper dz. And when we multiply and add all of these pieces up, this is going to be the total error in the volume when we're done, okay? So notice that things are pretty much scaled by like how big they are times your error, how big they are times your possible error, how big they are times the possible error. And we added those up in order to get our total differential or our total error, okay? So that's the kind of thing that we're looking to do here, all right? Now, they have to dress it up and make it all pretty here and make it like a difficult thing for us to do. But the initial thought here, okay, is that we are calculating the total error here, okay? So that's like the big application for this particular technique. So you know, pretty much chasing error in one bigger system, all right? So let's get started with a couple of exercises, because I know that that's nice that you've talked about it, but what are we doing here? Okay, so we have z is equal to 4x squared plus 5xy plus 9y squared. dz is equal to, well, the total differential, right? Let's just set this up. So we want the partial of z with respect to x times the differential of x, okay, plus dz partial of y, okay, with the derivative of y, okay, and that's what we're trying to do with all of this, okay. So that's what we're going to do here, okay. So let's go ahead and do that. So what is dz by dx? Okay, and that's going to be 8x plus 5y. Remember, we're taking the partial of x with respect to, or we're taking the partial of z with respect to x. Y is considered a constant for this, okay? But notice here the definition, we have the dx afterwards, okay? Plus, we have dz dy here, okay? So this is equal to 5x plus 18y. Okay, there's 4x squared. This is a constant as far as y is concerned. And then we have dy. Okay? And then we're going to go off and say, well, what was x and what was y? Because we need a specific spot here. So x is 9, y is -7. Okay? So we'll say x is 9, y is equal to -7. -7, that's terrible. -7. Okay, dx and dy, and we have to kind of give you all of these things. So in your experiment, you kind of have to know, like, what is the measurement error on the x value? What is the measurement or experimental error on the y value? Okay, so we're taking all these pieces together. Oops, 0.03, thank you. We're taking all of these pieces together to put them, you know, to put them all together here to get our total error. Okay, so that's what you could think of a total derivative as, right? So this is simply going to be 8 times 9 plus 5 times -7, right? That's this part here. Okay, dx was 0.04. Okay, and then we're going to add together. We have 5 times 9 plus 18 times -7. Okay, and we had, was it -0.03? I know I wrote negative. Let's just double check. -0.03. -0.03. Okay, and all we're going to do is add those up. Okay, that's all that's going to happen there. All right, so we have 8 times 9 minus 5 times 7 equals, okay, so this is 37. There's a 0.04 here, okay. What else do we have? We have 5 times 9 plus 18 times -7. We have -81 times 0.03 here, negative. Okay, and then we're going to go ahead and add these up. Okay, so we're going to say 37 times 0.04. Okay, negative times a negative, that's going to be a positive. So we have plus 81 times 0.03. Okay, we got it up with a 3.91. That's our total. That's our total derivative. Okay, this is dz written with a proper d. Okay, as opposed to something else. All right, so let's see what we got here. We got 3.91. 3.91, and we'll go ahead and check our answer. Okay, great. We'll move on to the next one. Okay. So next one up here. So let's take a look at this one. This one's a little bit more complicated. All right. So we have W is equal to, I wonder if I could do this. So let's do that and change this, kind of change the thickness down a little bit. W is equal to, I can't see that. Right? We can, but unless you have to squint the damn screen. So we have 7x squared plus 5y squared over z plus 3. Okay, so we do our differential here. We have dw, right? This is going to be the partial of w with respect to x, dx, plus the partial of w with respect to y, dy, plus the partial of z with respect to, partial of w with respect to z times dz. Okay, and notice they give us values for each one of these things. All right, so here we're going to go. Actually, I'll do one more thing. I'm going to say that w is equal to 7x squared over z plus 3 plus 5y squared over z plus 3. So the numerators you can separate. Okay, like think about this. If we have 4 quarters, okay, like you're going to do laundry, 4 quarters. I could have 1 quarter in one pocket and 3 quarters in another pocket, and I still have $1. Okay, but we can't do this with the top. If you have 4 quarters, I can't do something like this: 4 over 1 plus 4 over 3. I can't turn my 4, actual coin quarters into $4 and then 4/3 of a dollar. Like that doesn't work that way. Okay, just because I put my money in different pockets doesn't mean I somehow have more of it. Okay, be a lot easier for everybody involved, but that would not work. Okay, so the numerators you can separate, but the denominators you cannot separate, and this is why. Okay, and many of you might think like, well, why you're being patronizing? I'm sorry, I don't mean to patronize anybody. I'm not calling you out for it, but one of the things that I know is that you folks are going to be the people who are you're going to be the people that are good at math around you. Okay, and I want you to be able to say, oh, you can't do that, here's why. Okay, so my dw dz, this term here has no, dx, let's go in order. Okay, this term here has no x's in it, so this term here is a constant. This term here, like this part here, this is z plus 3, that's constant. So effectively what we're doing is we're taking the derivative of, okay, so you can think about it as like, let's put it way over here. Okay, we have like 7x squared over a constant, because z plus 3, as far as x is concerned, it's a constant. So let's put an a in there. A is a constant. So we have 7. This is 7 over a times x squared. And if I asked you to take this derivative, you'd say, hey, no problem. Okay, that's going to be 14 over a x's. Okay, so rather than look at this z plus 3 and get intimidated by it, because most people do. Okay, they'll look at this and they'll say, they got to take a moment to process this. And this is how I'm processing it. I'm saying, well, the z plus 3, like it's constant. It's 4 plus 3, 11 plus 3, whatever. But I'm thinking about it this way, and then I can just go ahead and take my derivative without having to worry about, like, well, what about the z? I don't even see it. It's an a or a b. It's a constant. So this is going to be 14 over z plus 3x, and then we're going to put in our proper dx here, okay? We're going to have our dw dy, okay? And again, our dy, like this term here, this is 7x squared over z plus 3, has nothing to do with y. So we only have to care about this part here, because the derivative of this is going to be 0. So we need 5y squared over a, right? And if I say, well, we have 5 over a y squared, take this derivative, you're going to say, oh, well, that's 10 over a y. No problem. Okay, so we're going to say this is going to be 10y over z plus 3. And then we're going to put a proper d for y next to it. Okay, because we're calculating, eventually we're going to be calculating total derivative. I'm doing this column right here. Okay, and then we need dz, or dw rather, dw over partial of z. So this is going to be a little bit more complicated. Okay, I'm going to go back to my original thought here, my original problem. The x squared and the y squared, those are constants. So really what we have is the derivative of a plus b over z, or z plus 3 rather, okay? And you're really not going to do it that way. You're going to say this is a plus b, z plus 3 to the negative 1, right? It's a bit of a harder derivative, but it's not too bad. So it's negative a plus b, right? Z plus 3 to the negative 2. Now, do I have to apply the chain rule? Yes, but the chain rule, the derivative of z with respect to z is just 1. Okay, so even though we are actually thinking chain rule, okay, that chain rule is 1. Okay, so the derivative here is a plus b over, there's a negative out in front here because of this negative right here, z plus 3 to the squared. Okay, because the negative 2 will go downstairs and then we'll be all set. Okay, so when I want to go back and write this a little bit more properly, right, we're going to say something like 7x, we're going to say negative 7x squared plus 5y squared, right, over z plus 3 squared with a dz this way. Okay, so this is going to be a little bit harder to deal with, okay, arithmetic wise, but it's not going to be too bad. All right, so here we're just going to plug our values in, right? We have what did they say to do? They said something like hey, dx was 0.05, dy was 0.03, dz is 0.06, and we're going to hope for the best here. Okay, so we have, okay, let's see if we can, wish I could push, can I make this smaller in a meaningful way? No, of course, because we got this thing down here. Yeah, it's not going to work. God forbid we would get rid of those things there. Okay, so let's just put in our numbers. We got 14 times negative 4, that's my x, divided by what's z? Z is 5 plus 3, and my dx is 0.05. Okay, we have 10 times y over, again, our 5 plus 3 times negative 0.03. Okay, right up here. Okay. Now this one's going to be a pain, right? Because we're going to have 7, well, we have a negative, okay? 7 times 4 squared plus 5 times, is that negative 3? No, it's just 3. 5 times 3 squared over 5 plus 3 squared, and then times negative 0.0, no, not negative, just positive, 0.06. Okay. Now we have some arithmetic to deal with. Okay. So we have our partial of z. Okay. So x dx here. Okay, all right, let's write that properly. So this is dw dx times dx plus dw dy times dy plus partial of w with respect to z times dz. All right. So arithmetic time. Okay. What is, right? 14 times -4, right? Divided by 5 plus 3 is 8. So divided by 8. Okay. Times 1/20 times 0.05. 0.05. Okay, so we get -0.35. Great. Just going to put that here and make a little note. This is -0.35 plus. Okay, now we're going to go up here, figure out our dy by dw by dy. All right, times dy, and we have 10 times 3, that's 30. 30 divided by 8, right? 5 plus 3 is 8. Okay, times -0.03. Okay, we get 0.1125. Okay, so this is -0.1125 plus, and then finally we do the last one. Okay, so we're going to come back up here and we're going to do something clever like exactly what it says. Okay, so we've got 7 times 4 squared. The hardest thing on this is honest, and this is all negative, by the way. So 7 times 4 squared plus 5 times 3 squared, this will be the top, divided by 8 times 8 squared is 64. Right? And then times 0.06. And we're going to remember that there's a negative sign in front of this thing, so we're going to write down -0.1472. Okay, because they wanted the 4 decimal places. All right, so just double checking 0.1125. Oh, that's excellent. Okay, so we just add these things up. So we're going to say -0.35 minus 0.1125 minus 0.1472. 1472. All right, and we have -0.6097. -0.6097. Okay, guarantee the hardest part of this problem is like the accounting and making sure that you have things added up in the correct spots. Okay, so the calculus on this, not really that terrible, but and there's one tricky part, right? That last one's a little tricky, but everything else should be okay. All right, so you get to the arithmetic, then it gets hard. All right, good question. Use total differentials to approximate the quantity. Then use a calculator to approximate the quantity and give the absolute value of the difference of the two results to 4 decimal places. All right, so what we're going to do here, okay, is we are going to say something like we have a z is equal to the square root, right? Technically we have 5.06 squared and 11.98 squared. Now 5.06, this is really close to a 5, and then 11.98, that's really close to 12. So what we're going to do is we're going to say this is z is equal to x squared plus y squared, okay, square root of. So z is equal to x squared plus y squared 1/2, okay? And we're going to say x is equal to 5 with dx equals to 0.06, okay? We're going to say y is equal to 12 with dy is equal to -0.02, okay? So I'm just saying, well, let's make these easier numbers, and then we'll adjust them with the d's here, okay? The numbers to the numbers we truly have, okay? That's what we're doing there. So this is, you guys, this is an application that we used to use this for, but this is the 21st century. You guys have phones in your pockets that are quite capable of doing this calculation. So this is not really a 21st century skill anymore, but it was a 20th century skill, and it was a 19th century skill. Okay, and we still use this for error calculations. So this is a good thing to be able to do, but this particular instance of this thing is not going to be that useful. Okay, so we want dz, sorry, this kind of dz, which is equal to dz by dx times the differential of x plus dz dy dy. Okay, and then we'll see what we go. My teachers always used to tell us things like, well, what if you're stuck on a desert island and you need to do this calculation? Okay, I think if I'm stuck on a desert island, I'm going to have more pressing issues to deal with. Okay, so what's the partial derivative here with respect to x? So we're going to have 1/2, right, x squared plus y squared to the negative 1/2, that's the derivative of my square root, times my chain 2x, the chain here is 0, okay? And then we're going to have our dx here, okay? Plus, same thing with y, right? Take the derivative of the square root function, it's 1/2 times the stuff inside, okay, to the negative 1/2, that's the derivative of the square root part, times what's the chain? The x part is 0, but the y part is 2y, okay? And then we have our dy, right? That's what we're doing here. So we have a little bit of cleanup to do, right? 1/2 and 2, that's that goes away. So we have x over the square root of x squared plus y squared dx plus the 2's cancel, so we have y on the top. The negative sends it downstairs, so we have the square root x squared plus y squared. Okay, by the way, this, you will not believe how, this particular kind of a problem I have done more times than I can count. This pops up all the time because it's the top of a sphere, okay? Well, it's not the top of the sphere, but the x squared plus y squared part is a circle, okay? So it's pretty much, we're looking at a cone type of a thing here. But you'll not believe like how many times I've had to do this particular problem. It's like countless, okay? So this pops up all the time. All right, what was our thing? Our x was 5, so we have 5 over, and we have square root of 5 squared plus 12 squared. And our dx, right, that was 0.06. Leave this to the end. Plus, what's our y? Our y is 12. We have 5 squared plus 12 squared, okay? And then what are we going up here? dy was negative 0.02. Okay, again, leave this part to the end. Okay, so we have 5 squared plus 12 squared, right? 5 squared plus 12 squared, that is equal to 25 plus 144. 25 plus 144 is 169, and the square root of 169 is 13. So we have 5/13 times 0.06 plus 12/13 times negative 0.02. Okay, at which point now I could think about dealing with the calculator. Okay, so here we go. We have 5/13, okay, times 0.06. I'm going to go ahead and just write it off right here. So this is 0.0231. Okay. And then we have a minus, because we have this minus, okay? And we have 12/13, 12 divided by 13, okay? And then times 0.02, all right? So we're gonna say this is 0. I lost my calculator, 185. So we're gonna round it, 0.0185. Right, and the negative is over here. So we're just going to add these up. Let's put a 0 here. Okay, that's, I missed a 0 in here, didn't I? Let's go ahead and put that in there. Okay, so let's see here. We've got 231 minus 185. 0.0, okay, so that's 46. Okay, so we're going to need 0.0046. Okay, this is what I did was say these were like in grams or something, and I just moved the decimal place. So 1, 2, 3, 4. Okay, 1, 2, 3, 4. So you could think about this as like 1, 2, 3. It's going to be 23 milligrams or 23,100 micrograms. Okay, 1, 2, 3. So 0.018.5 milligrams, and then we 18,500 micrograms. We're left with 46 micrograms. No, 4.6 milligrams here. Okay. So just making sure that if you're going to do that, make sure they're the same sort of order of magnitude, and it should work out okay. Now watch me put this in here and get the wrong answer. Okay, 0.0046. Okay, 4 decimal places, we'll check. You did not like that at all. Okay. Let's double check to make sure I didn't make an arithmetic mistake. So 0.0231 minus 0.0185. 0046. All right, that was not the mistake. Let's see. I'm gonna cheat on this one and say what's my answer, because I know, kind of hoping that it will. Not do that. Pause for a second. Figured it out. Okay. I forgot what is the goal that they asked us to do. They asked us to actually solve this. So we're going to say that we actually have to do this part, and then this is our error for it. Okay. So our function, our problem is 5 squared plus 12 squared plus our error. Okay, which is this guy. So the first answer should have been 13 plus, what is our total derivative? 0.0046. So that answer should have been 13.0046. When we go through and do the, let me just do it with a calculator, because again, we live in the 21st century. We just type in 5.06 squared, 11.98 squared, and get our answer, take our square root, and we get 13.00478. Okay, so our actual answer, 13.0048. So we are off by 0.0002. That's our error on this for doing our problem. Okay, so I looked at this and I said, oh, that's our error. Like, that's not, that's what we're adding to this thing to get our answer. Okay, not the answer. So I jumped the gun and said, oh, there's my answer. Like, no, that's my error attached to this 13. Okay, that's what the problem was. Okay, so that's our issue. Absolute error for the two differences, 0.0002. Okay, and that's what we're going to have for that. Okay, so something to remember is, like, don't forget what the original problem asked you, and then we should be okay. All right. So what I'm going to do is I'm going to go ahead and save this one, and so it will be about 30-ish minutes, and then we'll start on the next one, and we'll just do more of these. Okay, so there we go. All right, what are we doing? We are ceasing.